Hello friends, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video I am going to talk about spectroscopy. What is spectroscopy? It is the branch of science that deals with the study of interaction of matter with light, or it is the branch of science that deals with the study of interaction of electromagnetic radiation with matter. Electromagnetic radiations. Electromagnetic radiation consists of discrete packages of energy which are called as photons. A photon consists of an oscillating electric field and an oscillating magnetic field which are perpendicular to each other. You can see the source and directions, electric field and magnetic field. Electromagnetic radiations frequency. It is defined as the number of times electrical field radiation oscillate in 1 second. The unit for frequency is Hertz. 1 Hertz is equal to 1 cycle per second. Wavelength. It is the distance between two nearest part of the wave in the same phase, that is distance between two nearest crest and trough. Friends, electromagnetic radiations you can see here, wavelength and amplitude. The relationship between wavelength and frequency can be written as C is equal to nu lambda. You know, as photon is subjected to energy, so E is equal to h nu is equal to h lambda. Now electromagnetic radiations. You see the electromagnetic spectrum: radio, micro, IR, visible, UV, X-ray and gamma rays. Electromagnetic radiation, you see the white light passes through prism, dispersion angles, so violet, indigo, blue. Principle of spectroscopy. The principle is based on the measurement of a spectra of a sample containing atoms or molecule. A spectrum is a graph of intensity of absorbed or emitted radiation by sample versus frequency or wavelength. You can see there, a spectrum is an instrumental designed to conform the compound. Friends, absorption spectroscopy, an analytical technique which concerned with the measurement of absorptions of electromagnetic radiations. UV 185 to 400 nanometer, visible 400 to 800 nanometer, spectroscopy, IR spectroscopy 0.76 to 15 micrometer. Emission spectroscopy, an analytical technique in which emission of a particle or radiation is dispersed according to some property of the emission and amount of the dispersion is measured. Example, mass spectroscopy. Interaction of EMR with matter, electronic energy level. At room temperature, the molecules are in the lowest energy level, E0. When the molecule absorbs UV visible light from EMR, one of the outermost bond lone pair electron is promoted to higher energy state, such as E1, E2, En, is called the electronic transition, and the difference is as E is equal to del E is equal to h nu En minus E0, where N is equal to 1 to 3. Friends, vibrational energy level, these are less energy level than the electronic energy level. The spacing between energy level are relatively small, that is 0.01 to 10 kilocalorie per mole. For example, when IR radiation is absorbed, molecules are excited from one vibrational level to another, or it's vibrate with higher amplitudes. Friend, rotational energy level, these energy levels are quantized and discrete. The spacing between the energy levels are even smaller than vibration energy level. So daily rotational, vibration and electronic. Now friend, Lambert's law. When a monochromic radiation is passed through a solution, the decrease in the intensity of radiation with thickness of the solution is directly proportional to the intensity of incident light. Let 1 be the intensity of incident radiation and x be the thickness of the solution. Then Lambert's law is equal to minus di by dx, directly proportional to I. So minus di by dx is equal to ki. Integrate equations between limits I is equal to I naught at x is equal to 0 and I is equal to I at x is equal to 1. We get ln I by I naught is equal to minus ki. Lambert's law 2.303 log I by I naught is equal to minus kl. Log I by I naught is equal to minus k by 2.303, where log I naught by I is equal to A absorbance at k divided 0.303 is equal to E absorption coefficient and A is equal to EL. Lambert's law. When monochromatic radiation passes through a solution, the decrease in the intensity of radiation with thickness of the solution is directly proportional to the intensity of incident light as well as the concentration of the solution. Let be the intensity of incident radiations and thickness of the solution, C be concentration of the solution. So you can see here Beer's law, minus di by dx directly proportional to ci, so di by dx is equal to kci. Integrate equation between limits I is equal to I naught, x is equal to 0, I is equal to I at x is equal to 1. So we get ln I by I naught is equal to minus k prime c 1 c l. Beer's law 2.303 log I naught by I is equal to kcl. Log I naught by I is equal to k divided by 2.303 cl, where log I naught by I A absorbance, k 2.303 is equal to E molar extension coefficient and A is equal to ECI Beer's law. So A is equal to ECI, T is equal to 1 by I by I naught or minus log T is equal to log I by I naught is equal to absorption. From the equation it is seen that the absorbance, which is called as optical density OD of a solution in a container of fixed path length, is directly proportional to the concentration of a solution. So what is the principle? The UV radiation region extends from 10 nanometer to 400 nanometer and the visible radiation region extends from 400 nanometer to 800 nanometers. Near UV region 200 nanometer to 400 nanometer, far UV regions below 200 nanometer. For UV spectroscopy study under vacuum condition, the common solvent used for preparing samples to be analyzed is either ethyl alcohol or hexane. So possible electronic transitions can graphically shown as the possible electronic transitions are sigma star transition. Sigma electrons from orbital is excited to corresponding anti-bonding orbital sigma star. The energy required is large for these transitions. Pi star transitions, N to sigma star transitions, N to pi star transitions. So sigma to pi star transition and pi to sigma star transitions. These electronic transitions are forbidden transition and are only theoretically possible. Thus N to pi star and pi star electronic transitions show absorption in the regions above 200 nanometer, which is accessible to UV visible spectrophotometer. Now friend, chromophore. The parts of the molecule responsible for inverting color are called chromophore. The functional group containing multiple bonds capable of absorbing radiation above 200 nanometer due to N to pi star and pi star transition. The interpret UV visible spectrum following points should be noted. Non-conjugated alkenes show an intense absorption below 200 nanometer are therefore inaccessible to UV spectrophotometer. Non-conjugated carbonyl groups compound give a weak absorption band in the 200 to 300 nanometer region. So acetone, which has lambda max 279 nanometer, and cyclohexane has lambda max 291. The double bond are conjugated in a compound. Lambda max is shifted to longer wavelength. You can see here. Now oxochrome, the functional group attached to chromophore which modify the ability of chromophore to absorb light, altering the wavelength or intensity of absorption, or functional group with non-bonding electrons that does not absorb radiation in a UV region, but when attached to a chromophore alter the wavelength and intensity of absorption. You can see. So bathochromic shift, red shift, hypsochromic shift, blue shift, hyperchromic shift, effect, and hypochromic effect. What is the bathochromic shift? When absorption's maximum. What is batho? In alkaline medium, nitrophenol shows red shift because negatively charged oxygen delocalizes more effectively than unshared pair of electrons. When absorption maximum of a compound shift to shorter wavelength, it is known as hypsochromic shift or blue shift. The effect is due to presence of any group causes removal of conjugations or by the change of wavelength. Anilines show blue shift in acidic medium, it loses conjugations. Hyperchromic shift effect when absorption intensity epsilon of a compound increases, it is known as hyperchromic shift. The oxochrome introduced to the compound, the intensity of absorption increases. So hypochromic effect when absorption intensity of a compound is decreased, it is known as hypochromic shift. You can see naphthalene and 2-methyl. So this is the shift and effect, hyper, hypo, red shift and blue shift. What is the application? Quantitative and qualitative analysis. It is used for under characterization aromatic compounds and conjugated olefins. It can be used to find out the molar concentration of solute under study. Detection of impurities is one of the important methods to detect impurities in organic solid. Detection of isomers are possible. Determination of molecular weight using Pearson. These are the references. Friends, hope this video will be helpful to you. If you like this video, then subscribe my channel and